Okay, good morning. Well, last a few minutes, actually several minutes. So let's get into our topic of superposition right away. Section 2 in superposition. Okay, so introduce the topic of superposition, and I stated that we could take a large complex circuit and apply superposition to it by breaking it into multiple parts or multiple pieces, and then analyze each part independently. And the number of parts, well, depends on the number of sources we have in there. So if a circuit has n number of sources, we can break it down into n number of parts. N number of independent sources, not dependent. Dependent sources are the diamond-shaped ones. Those cannot be reduced to zero or removed from the circuit. Okay, so the way we do that is by reducing all independent sources to zero, except for the one that we wish to analyze. Okay, so in this example, we had a voltage source and a current source, two sources, so two separate circuits, two separate analyses. First one, we have a voltage source reduced to zero, and we analyze the circuit solely for the current source working or active at a time. Okay, in the next circuit, circuit number 2, voltage source is active, current source is inactive or reduced to zero. And the way to do that is by replacing a voltage source with a short circuit and a current source with an open circuit. So you do this n number of times. If there were 3 sources in there, doesn't matter whether it's a voltage, current, or a mixture of both, or a mix of both, you analyze the circuit n number of times. So is that clear to everyone? Superposition principle. Any questions regarding the explanation? Okay, so then let's take a look at an example. Here we are asked to find the current I2 using the principle of superposition. We could apply node voltage analysis, mesh current analysis, or we can apply superposition. When it is a circuit like this, again, simple circuit, we have 2 sources, 3 resistors, not a lot of components. So any one of the 3 analysis methods will do the job. Okay. So let's see how we would solve this using superposition. So circuit setup, R1 is 5 ohms, R2 is 2 ohms, R3 is 4 ohms. I2 is coming down from the top between 2 and 4. R3 and R2 are in series. They're connected by one junction right here at the top right corner of the circuit. We could possibly reduce it by combining R2 and R3 together. Okay, but for now, I'll just leave it as it is. Current source IS is 2 amps and VS is 10 volts. Okay, so let me set up the problem first. What I will say is, if VS is active, I'm going to note it as circuit A, and hence the current I2, because of voltage source VS, I will note it with a subscript of A, I2A. And when you are solving and doing a setup of the problem, you can use any notation you want. Okay, so this is just the notation I'm using. And similarly, if VS is active, if IS is active, I would call it part B or circuit B. And current I2, due to IS working alone, is we I2B. So I2B. Okay. So in order to find one quantity, one current or one voltage, you have to divide the circuit and analyze it n number of times. for each and every source. So the actual current I2 would be a summation of I2A and I2B. Let's take a 10-second pause. Let me know if you have any questions. Make sense? If there was a third source in there, I would have I2C. Fourth one, I2D, and so on and so forth. And you can see how it can get complicated real fast. Well, not complicated, but lengthy and time consuming, the more number of sources you have. You good so far? All right. So then let's draw the circuit for A. Only Vs is active. All other sources in the circuit have to be reduced to 0. The only other source in the circuit is Is. So you replace Is, you reduce Is as 0 to reduce a current source to 0, meaning replace it with an open circuit. Right? So Is is equal to 0. Replace with an open circuit. And so my circuit now becomes like this. That's Vs. If you replace it with an open circuit, you don't even have to draw out these terminals. You can leave them off the circuit. You don't have to draw them out. Okay. This is just for illustration purposes because this is the first example. And I have I2A coming down. This is R1, R2, and R3. So right here, you can see an advantage or the purpose of applying superposition. What do we see? What is the relationship between R1, R2, and R3? They're all in series, right? Because the current source is reduced to 0. It's not part of the circuit anymore. R1 and R2 are joined together at the top node. The top node used to have a connection, but because it is not connected to anything, obviously current cannot go through here. And so it's in series. Makes sense to everyone, right? And because they're in series, it's a one-step answer. I can write I2B, simply apply Ohm's law, V equals IR, I equals V over R. And so I2B is Vs over Req, the total equivalent resistance, which would be Vs or R1 plus R2 plus R3. Vs is 10. R1 plus R2 plus R3 is 5, 2, 7, 4, 11. And therefore, I2B is 0.909 amps. Yes. Oh, yeah, it's I2A. Thank you. 10-second pause. Think over it. Let me know if you have any questions. Any questions at all? Straightforward. Right. Obviously, again, this is a simple circuit. You only have two sources in there. But if you have more than 2, 3, 4, then things could take, a different turn. All right, then let's come over to the left here and analyze the circuit for the current source. So circuit B, IS is active. That means I reduce Vs to 0, which means replace Vs with a short circuit. So this time, and this is a very interesting circuit. You'd be surprised at the answer at the end. So IS is coming down. We have R1, R2, R3, and I2B this time. Okay. Take a few seconds, look at the circuit, see if it makes sense to you, right? It's a current source being active. The other source in the circuit is a voltage source. So you replace it with a short circuit. What happens to the circuit now that we have replaced it with the source? What do we see? Take your time and think about it. R2 and R3 are not altered in any way. They are still in series. How about R1? What happens to R1? It is parallel. Anyone else? So R1 is connected to R2 at the top. And then, of course, R2 and R3 are in series. So you have two nodes right here. Let's call them 1 and 2. So if we take and combine these two together, R2 and R3, they form one single resistance, which are connected between 1 and 2. The current source is also between 1 and 2. And then R1, because of the short, is also connected between 1 and 2. So all three components are in parallel. Okay. So this circuit can be redrawn like this. IS, this is R2 plus R3. And that is what? 4 plus 2, 6. And this, of course, remains R1. Does that make sense to everyone? Any questions? Keep in mind, every circuit is different. So you have to proceed step by step, okay? Depending on the circuit connections, depending on the number of sources in the circuit would change, completely different, and it would be completely different from what what the original circuit is. So you always have to take it step by step, draw out the circuit for every change that you make, and then, it'll make more sense. So in this case, as I said, simple circuit, we take the voltage source out, replace it with a short. That creates a parallel line for R1 with the current source. Then the next point or the next question is, what happens to current in a parallel circuit? It's coming down this pathway. Some of it goes down here. Some of it goes down here. What is happening? Current is being divided, split. So you can apply current division. At this point, you can apply any technique you want. You can reduce the entire circuit to just one single resistor, apply Ohm's law, find the total voltage between 1 and 2. Or if you want to skip those steps, we apply current division directly, which is the same thing. Current division is derived from Ohm's law. And so you can apply current division directly. Or you can do this. Now this is still I2B, but this current will not be I2B, okay? This is REQ, and this REQ is R1 in parallel with R2 plus R3. The terminals still remain the same. This is 1, this is 2, and this REQ, again, R1 is, what is R1? 5, 5. So 5 in parallel with 6. 5 times 6 is 30, divided by 11. Should give me 2.73 ohms. Parallel, parallel, REQ. I can apply current division directly here. I would still need REQ for that, or draw out one more step, REQ. Current source IS times REQ would give you the voltage across 1 and 2. Then once you have voltage, because it is a parallel circuit, the voltage across IS is the same voltage across R1, is the same voltage across R2 plus R3. Then apply Ohm's law one more time, and you obtain the current I2B. I will show both ways. So this is IS. Apply Ohm's law. So from here, from Ohm's law, I can write V12, voltage measured between 1 and 2 is IS times REQ. IS is, what is IS? 2 amps. 2 times 2.73. 2 3s are 6, 2 7, 54, 5.46 volts. Right? 6, 2 7, 14, 4 and 5, 5.46 volts. 5.46 volts is across R1, across IS, and also across the 6 ohm combination. You guys with me so far? And then I can write I2B is V12 do this on a calculators. What do you get? .909. .909. If we applied current division, I'll show you the equation for that. Instead of applying the 2 steps, if you apply current division, I can write the current going down. Let's see. Let's call this IR3, okay? IR3 is equal to, it's a fraction of IS. The fraction is given by the ratio of REQ to the total resistance in that branch, so R2 plus R3. IS is 2, REQ is 2.73. and this is 6. We solve this, you get the exact same answer. Okay, you get the exact same answer. Current division and voltage division are derived from Ohm's law. They allow you to skip a couple of steps. So instead of doing this and this, you can directly write down the answer in one step, in one equation. All right, 10-second pause, think over it. Let me know if you have any questions. Any questions at all? Did the solution make sense? Okay. Well, that's the total resistance in that branch. So R2 and R3 are the total resistance in that branch, which is 6 ohms. I did not give a notation for that, so that's why I wrote it as R2 plus R3. But let's say I called it R4, then it's the same current flowing through both resistors. All right, any other questions? Okay, let's take a look at the circuit. Job's not done yet. What do we see? Specifically, IR3 and I2B. They are in opposite directions. So what is the value for I2B? This should be IR3. I2B is equal to, if you have two notations for the same current, but they're in the opposite direction, what does it mean? Sorry, what? No. That's the I2. I'm not talking about I2 just yet. I'm talking about just these two currents. This is plus 5 amps. If it's coming in the opposite direction and you just mention opposite direction, minus 5. And so your final answer is correct. This would be minus IR3. The point here is you have to be careful with the direction of the voltage sources and the current sources. And so this becomes minus 0.909 amps. And I2A was plus 0.909. And so my actual I2, which is a sum of I2A plus I2B, becomes 0.909 is 0. If the current source was in the opposite direction, you would have had a different answer. It would be 0.909 plus 0.909. But because it is going down, it's forcing another current through there. So the potential difference between the 2 points comes out to be 0. So there is actually no current flowing through that path. All the current is just flowing to R1. All right, any questions? Everybody understand? Does everybody understand the process, the step? All the steps that are required? Any questions at all? And again, this is a simple circuit, only 2 sources, but you could practice with a circuit that has 3 sources or any other circuit for that matter. Also, as practice, I would recommend, since we already know the answer to this, practice using node voltage analysis and mesh current analysis. Okay. Practice using node voltage analysis and mesh current analysis. Yes. No, you can solve any circuit with all three methods. Yeah. The basic premise of using superposition is that the circuit becomes simple to analyze, as we can see here. But the whole point of doing node voltage and mesh current is that some circuits are not reducible down to one single resistance. So it may be that we have superposition, we apply superposition to a circuit. Instead of having a circuit like this, we might have a circuit that we cannot reduce to a single resistance. So then instead of just doing Ohm's law like we did here, we might have to end up applying like node voltage or mesh current analysis, which kind of defeats the purpose of using superposition. Does that make sense? Right? The whole point of using superposition is so that the circuit is simpler to analyze. But if after applying superposition, we still have to apply NVA or MCA, then it just doesn't make sense to use superposition.
Do you think you could scroll back down, please?
Sure. All right. And again, if students haven't signed up for the class notebook, I know some students haven't, these annotations would appear in real time at your end. Okay, any questions? Any questions at all? Okay. All right. So superposition topic was introduced on Wednesday, covered the theory and the example today. So consider the homework assigned. I won't make it due over the weekend because Monday is a quiz. Well, actually, you know what? Monday's a quiz. So, and the quiz will be on mesh current analysis, but I might slip in superposition in there. Not an entire problem, just the basic concept. Short answer questions, kind of like that. So the homework I might make due like Monday night. So you'd have what, Friday, Saturday, Sunday, and Monday. Just a little bit shy of 4 days to get that done. But there are only 2 problems in there. So it doesn't take a lot of time. The average time based on my past or previous experience and previous data has been less than like, it's between 20 and 30 minutes to do the superposition homework. So again, open it up, take a look at it. There are 2 problems in there. If you need help, I'll be available over the weekend. Available today. I'll be available via Zoom over the weekend. And then we'll make this superposition homework due on Monday. Okay. All right, from here, this is the end of all the analysis techniques that we have to learn for this class, for chapter 2. Now we're going to take all of the techniques that we have learned and apply it to a larger circuit, to a larger principle. Let's say you are a circuit designer, well, not circuit designer. Let's say part of your duty for a project is to design a circuit or find the value of a component. Okay. You're asked to find there's an application, you're asked to find the most optimum value for a resistor R6 in this example. Okay. You're asked to find the value for the voltage across R6. So what technique do you think you would use? Three sources in there. What comes to mind? We got multiple nodes, node voltage analysis. We have 3 meshes. You can apply mesh current analysis. 3 sources. You could also apply superposition, right? But your job as a designer is to find the most optimum value. So you would analyze the circuit once, whatever technique you use doesn't really matter, and you would find VR6. Let's say you found VR6 for value for R6 was, let's say, 10 ohms. And you need to get this VR6 within some specification, right? So you don't have to write this down. This is just for explanation purposes. Okay. So R6 was 10 ohms. You did your entire analysis might take you like, half an hour to get it done, just because the circuit is, it has a lot of components and multiple sources, and you find the value. But then your boss comes in and tells you, this is not good enough. We need to change the value to R6 to do it even better because it doesn't work for our project. And now you change the value for R6 to, say, 15 ohms. What do you have to do? You have to do the analysis all over again, right? All over again, multiple times. So this is a real problem that is encountered by circuit designers. Okay, you have to find the optimal values for every single component in your circuit. And nowadays circuits run into millions and billions of components, right? So you'd have to sit there and just keep doing this analysis again and again and again and again. Well, in order to not do that, there was a, I want to say it was a French telegraph engineer, Charles Thevenin. He postulated a theory saying that if you wanted to find the optimal value for a voltage or current through a component in a circuit, you could analyze it by removing that component from the circuit and find the voltage between the open terminals. And that voltage would remain constant, irrespective of the value of that component itself. Okay, so theory was, if you want to find the voltage across R6 for multiple values, you simply remove R6 from your circuit, analyze the rest of the circuit without that component, meaning without R6, find the voltage across the open terminals, and also find the resistance between the open terminals. And that would remain constant no matter what the value of R6 was. And that theorem came to be named after him, known as Thevenin's theorem. Okay, Thevenin's theorem. Oh. So the theory goes, or postulates, that you could take this entire circuit outside of R6 and represent it with a single voltage source and a resistance in series between those open terminals. So if the terminals were here, actually, yeah, that's not good. Not visible. This out plus and out minus is simply a notation, okay? It could be X and Y, it could be A or B, it could be anything. But it simply states you analyze the circuit without that component, and you can represent the entire circuit with a single voltage source in series with a resistor between those open terminals. Okay, between those open terminals. And that is the Thevenin theorem. And this equivalent circuit is known as the Thevenin equivalent circuit. It is not an analysis technique. Okay, it is not a new analysis technique. You will simply apply the techniques that you have learned so far in order to represent the circuit as a Thevenin equivalent circuit. It's important to note that. It is not a new analysis technique. It is simply a representation. Few years later, there was an American engineer. I think he was working for like Bell Labs, working with a lot of telephone equipment. So they use a lot of current sources in there, current amplifiers. And he found his own version of the theorem. His name was Norton, Andre Norton. No, Edward Norton. Edward Norton, not the actor, just the same name. And he postulated that it is possible to represent the exact same circuit in terms of a current source in parallel with that resistance between those same open terminals. Okay. So his theorem was a derivation of Thevenin's theorem. And the reason he had, because it is more useful for him to represent the circuit as a current source. So his theorem postulated that you could take the component out and represent the rest of the circuit as a current source in parallel with a resistance between those same terminals. And that came to be known as Norton's theorem, or Norton equivalent network, or Norton equivalent circuit. So Thevenin circuit. This is Thevenin circuit. This is Norton circuit. VTH is the Thevenin equivalent resistance, voltage. And so VTH is Thevenin voltage, VTH. Again, it is a source, okay? It is a source. RTH is Thevenin resistance. And IN is the Norton current. Note that the Norton circuit has the same Thevenin resistance. Sometimes people like to refer to that Thevenin resistance as RN, Norton resistance, if they're working with Norton current. But it means the exact same thing as RTH. If you look at a different book, different authors like to use their own notation. So VTH could be represented as just VT or uppercase T. It could also be uppercase T with an H, VTH. So it just depends on who the author is, who is writing, but it's simply a notation. In this kind of circuit, if you see VT, it is referring to Thevenin voltage. If you see RT, it's referring to Thevenin resistance, and IN refers to Norton current. Okay. So the advantage for this, advantage of doing this kind of circuit, let me sum it up here. Let's say you analyze a circuit and you find R6 was here, right? So R6 would plug back in at those output terminals. This is RT, and you found VTH as, let's say, 10 volts. And you found RTH as, let's say 10 ohms, just to keep things simple. Now, if you want to find the voltage across R6, VR6, it is a one-step answer. Think about it. What can we apply? What principle can we apply to find the voltage across R6? Everything's in series. When you apply voltage to a series connection of resistors, current remains the same, but the voltage gets divided. You can apply voltage division. So no matter how many times you change the value of R6, every single time for every single value, your VR6 is a one-step answer. VR6 from voltage division would be VTH times R6 over REQ. REQ in this case would simply be RTH plus R6. So you could take like 100 different values for R6, put it in a spreadsheet or a calculation software like MATLAB, plug in as many values as you want, just give you answers for all of them all at once. Make sense? You don't have to sit there and analyze the circuit over and over and over again for every single value of R6. And that is the purpose and the advantage of using Thevenin equivalent circuit. And same thing with Norton current. If you wish to find the current through R6, you can find the Norton current, simply apply current division and find find IR6, the current through R6, for as many values of R6 as you want. All right, any questions about this theorem? This is the last and the most important topic in circuit analysis, Thevenin and Norton equivalent circuits, or some other references would state it as Thevenin and Norton equivalent networks. Circuits and networks in this case are synonyms of each other. Okay. Any questions? Any other questions? Does the concept make sense? Again, this is a 30-point problem on the final exam. Okay. This 30-point problem, of course, has sub questions in there, but it will run into like 4 pages. Yes. This R2, that has nothing to do with RTH here. It's just a separate analysis. And we'll see that when we get to an example. So there are steps that we take to determine RTH and VTH and the Norton current. And so we'll look at all of that next week. Yeah. So as it stands, each component alone has no bearing on RTH. They are all working together, and that's how we'll find RTH. Yeah. Okay, we'll end class here today. I'll see you all on Monday. Have a good weekend. Again, if you have any questions, I will be available. Quiz on Monday as usual. Topic will be mesh current analysis and perhaps some concept of superposition. Okay. Stop.